In this lecture, I'll be briefly talking about two techniques, parallel imaging and simultaneous multislice imaging. In looking at the radio frequency or RF technology, one feature of the radio frequency coils is that as they get smaller, they generally have better signal-to-noise characteristics. And in particular, they have really good signal-to-noise close to the object, close to the coil, and it falls off as you get further away from the coil. However, if we place multiples of these coils around the object being imaged, for example, the brain, we can actually, with the sum of all of these, get much better signal to noise, even deeper into the structure, like in the middle of the brain. And that's illustrated at the lower left, where there's a comparison between a 16-channel array coil compared to a single-channel, much larger birdcage coil. And you can appreciate the improvements in the signal to noise. Now, one of the challenges with acquiring data from multiple coils is that you have to rapidly digitize and amplify each of these signals separately, and that can add quite a bit of cost. Now, fortunately, these analog to digital converters have come down quite a bit in price, in part due to the cell phone industry. So work from colleagues of mine at the National Institute of Health were able to use these boards that were developed initially for the cell phone industry and put them together in order to acquire the images that you see on the bottom left. Now, of course, acquiring the data at higher signal-to-noise ratio is great, but it also allows us to trade that signal-to-noise for other purposes, for example, to acquire the data at higher resolution. One of the challenges with collecting data at ever-increasing resolutions is that during the time that we're acquiring the data, for example, using this echoplanar image acquisition, the signal is decaying, the T2 star decay. So at some point, we have very little signal left, and even if we were to acquire more and more data, which we'd need to do if we wanted to get higher and higher resolutions, there really wouldn't be any signal left. One way around this is to use what we call parallel imaging. So on the top right, I show an example of scanning through K-space, every line, and if you do a Fourier transform of that, you get the image that's shown to the right of that. However, if we skip every other line in K-space, or skip multiple lines in K-space, as you recall from the electron K-space, what that does is it wraps up the image. That is, the image gets aliased in that direction, in the phase encoding direction. However, we can use these sensitivity profiles of the coils to help in terms of unwrapping these images. More specifically, the coils that are at the top of the phantom will see the areas that are closest to it brighter, and the parts of the phantom that are furthest away from it less bright. But in contrast, the coil that's at the bottom will see the bottom of the image brighter and then less so as it falls off. So by using the multiple RF coils, each of which has a different sensitivity profile, we can combine these with some linear algebra and be able to unwrap these images, as shown in the bottom right. We can reduce our imaging time by a factor of whatever our acceleration is. So if we are skipping every other line in K-space, our acceleration would be a factor of 2. So we're reducing our imaging time for a factor of 2, or we can use the same amount of imaging time to increase our resolution. It also reduces the amount of distortions by a factor of 2 if we keep the same resolutions. But it does come at a cost of the reduction in signal to noise at about a square root of the reduction factor. So if we're doing an acceleration of 2, it'd be a square root of 2 reduction in SNR. Finally, another technique that is becoming more and more popular now is what's called simultaneous multislice imaging, or multiband imaging. The idea here is that instead of just acquiring one slice at a time, we could excite and acquire 2 slices or multiple slices at the same time. And you end up getting an image what's shown here on the right, a superposition of those 2 slices. However, if we have multiple radio frequency coils, then as shown here on the left, then the coils at the top are going to see the topmost slice brighter than the one below it. And in contrast, the coils at the bottom are going to see the bottom slice brighter than the top slice. So using information from multiple coils, we can actually unwrap these images. Now, one additional modification we can make is you can place some additional pulses to cause one of the slices to be aliased. And in that case, you can see that they're also in the image separate from one another, and this aids in terms of unwrapping these 2 images. And again, we would see the differences in the intensities based on the differences of these 2 coils. And this simultaneous multi-slice imaging is actually being used right now in 2 very large projects. One, the Human Connectome project that just finished acquiring data from about 1,200 participants, and the larger Adolescent Brain and Cognitive Development Study, which is acquiring data from almost 12,000 adolescents throughout their development. So you're going to be seeing these sequences